Good morning. We continue today with our discussion of the um, simple MOSFET current mirror. Um, Last time we looked at the circuit and we showed that this circuit can provide us with a constant current, and therefore we can consider it to be a constant current source. And we also considered the case when there is a channel length modulation, so there is a VA, and in this case, the current would have a dependence on the output voltage, so it's no longer a perfect ideal current source. We derived the expression in this case, and this is what we get. The equation shown, IO will be W over L2 divided by W over L1 times IRF times 1 plus VO over VA2 divided by 1 plus VGS over VA1. And if I look at this expression and I verify it by circuit simulation or by full analysis of the circuit, then this is the curve that I would get. This is a simulation that shows me how does the output current vary with the output voltage for all values of VO. Now, is this good news or bad news? Well, let's see, let's analyze. First, how would an ideal current source look like? An ideal current source will give me a current that does not depend on the voltage, and therefore an ideal current source would have such characteristics, the horizontal ideal line. So this ideal line is horizontal. What does this mean? It means that current doesn't change. It's at this fixed level. So if the current is at this fixed level here and does not change with voltage, that would be an ideal current source. So horizontal is the ideal. But I'm getting this curve. Now, another limit that I have and that we talked about last time is that this region here for the output voltage less than VOV, this is an important limit here, VOV. If the output voltage is less than VOV, it means that VDS of Q2 is less than VOV, and Q2 will no longer be in saturation, and the whole equation will no longer apply. So I will call this region where the output voltage is less than VOV the forbidden region. I shouldn't really operate there. I'll be operating the circuit outside the region where it's applicable. So let's forget about this. And now let's compare the ideal here with what I get. Now, this is almost like a straight line, and this is also a straight line. This has a non-zero slope, while this has a zero slope. So ideally, I would like to have no slope, no increase in IO whatsoever, but because of VA, I will get this increase. Now, one way to measure how far I am from ideal is to see how large is the slope. If the slope is very large, then I'm far away from ideal. If the slope is close to zero, then I'm close to ideal, and this is a pretty good circuit. So let's see, how can we measure the slope? One way to measure the slope is actually to compute the output resistance of the circuit, which is delta VO over delta IO. The slope really is delta Y over delta X. That's delta IO over delta VO. But we don't find it directly. We find its inverse, and we call this the output resistance. So we find delta VO over delta IO. It's kind of related to the calculation of output resistance for amplifiers. So delta VO over delta IO is what we can show, and it's shown on the next slide, that this quantity is VA2 divided by half K prime W over L2 VOV squared. So if I take the equation here, if I take this equation and I calculate delta VO over delta IO, then I get this quantity. But what is this quantity? This quantity is exactly small RO2. If I want to calculate small RO2 without thinking about output resistance or whatever, just small RO2, then this is the formula for small RO2. And the output resistance capital RO is this, and therefore it's equal to small RO2. All right, so I'm close to ideal if the slope is 0. RO is not the slope, RO is 1 over the slope. So what would be the ideal value of output resistance for a current source? If the ideal value of slope is 0 and RO is 1 over the slope, then the ideal value of RO would be infinity. An infinite output resistance would be an ideal output resistance for a current source. So the larger the RO is, the better. This is just a quick proof of the result on the previous slide. If I take the expression for IO and expand it and find delta VO over delta IO, then I get this, what we got on the previous slide. All right, so output resistance is a nice way to see how far I am from ideal. And what does it mean really? What delta VO over delta IO? If the current source is ideal, then IO should not change. If I have an ideal, perfect current source, its current should be fixed. And I should not see any delta IO. Delta IO is a change in IO. IO should not change, and therefore delta IO should be 0. So if VO changes, say VO is here at 4 volt, and it changes to 5 volt. So delta VO for this would be 1 volt. That's delta VO of 1 volt. For the ideal case, IO does not change with that, and delta IO is 0. So what would be the output resistance? 1 volt over 0, and therefore infinity. And this is the ideal case. Output resistance is infinite. However, for the real case, if VO increases from here, from 4 volt to 5 volt, then the output current would increase a bit by small delta IO. And this delta IO is this increase in current from this point to this point. So I will have some delta IO when the current source is not ideal. So maybe a few microamps, let's say. And therefore its output resistance will not be infinite. It will be 1 volt over whatever, 2, 3, 4, 5 microamps. So this will be the output resistance of the non-ideal current source. So this is how we can measure or estimate how far or how close we are to the ideal case. Let's do an example. Let's take this same circuit and say VDD is 3 volt. IRF, the current flowing on the left half of the circuit, and the resistor is 100 microamp. And we want to design for IO also 100 microamp. So I want to create a current source that will give me a current of 100 microamp. Q1 and Q2 are matched. They have L equal 1 micrometer, W 10 micrometer, VT 0.7, K prime N 200 microamp per volt squared. And do not neglect lambda in DC analysis. So include VA in the DC analysis. All right, so this is what you want to do here. Just to remind you that this circuit is supposed to be connected to something. So this is something that's connected to the circuit. So I will call this rest of circuit that I am not showing. Okay, so ROC, rest of circuit. So there's something connected here, and that's why this line is dotted. And this circuit the resistor and the two MOSFETs, this is creating a current source. So the rest of the circuit, so if this is the rest of the circuit, ROC, feels as if it's connected to a current source, which is IO. All right. So if you're sitting in the rest of the circuit, you feel as if whatever is connected below, which is the current source here, is this IO, is this current source. So now we want to design, I want to make this IO 100 microamp. And I want to find the quantities. So let's do that. So I want to find, if I want to design, I want to find the resistor, which is the only unknown, and then find the lowest VO for current source operation. So VO would be the voltage here. This is the output node, and VO would be the voltage here. So how low can this voltage be while maintaining current source operation, while this is almost constant? And given VA prime equals 20 volt per micrometer, find the output resistance of the current source and find the change in the output current in IO when the voltage at the output node changes by +1 volt. So 1 volt is delta VO, is the change in VO. All right, so let's see, let's start with the solution. That's my circuit, and I'm given that I need to include VA in the DC analysis. So since I'm told to include it, I will show it. I will show the correction factor. And this is the equation now for Q1, MOSFET Q1 in SAT. ID1 is half K prime W over L1, VGS minus VT squared. And then times, because I have to include VA, 1 plus, this is supposed to be VDS1 over VA1. But what is VDS1? VDS1 is here, and this is exactly equal to VGS. So this is VDS1. And because of the short circuit, this is equal to VGS. So VDS1 is VGS. And this is what we have here, VGS. Now, I'm given that IRF is 100 micro. That's given. And I have the other quantities. I need first to find VA1. VA1 is VA prime times L1. VA prime is 20 volt per micrometer. L1 is 1 micrometer. So 20 volt. So that's VA1. And then 100 is the given current. IRF is 100 micro. It is half K prime N W over L1. So half K prime would be also equal to 100. W over L is 10. VGS, I don't know what VGS is. I need to find it. Minus VT, 0.7 volt, squared times 1 plus VGS over 20. So now I need to solve this to find VGS. And this is a cubic equation. I can solve it on my calculator. And if I do that, I will get a VGS almost 1 volt, 1.008 volt. So that's VGS. And this is the VGS for Q1 and Q2. The two MOSFETs have the same VGS. So that's VGS. And now it's easy to find the resistor value. Because VGS is the voltage that appears at the drain of Q1 also, R is VDD minus the voltage at the drain of Q1. The voltage here at the drain of Q1 is VDS1, which is also equal to VGS. So VDD minus VGS, 3 minus 1.008 over IRF, the current flowing in the resistor. And that's almost 20K, 19.9 kilo ohms. So that's the resistor value. Now I need to find the other things. I'm asked about what is the minimum VO and the output resistance and the change in the output current. So let's start with the minimum output resistance. We know that the minimum output resistance, minimum output voltage or minimum voltage at the output node here This should never drop, because this is equal to VDS1. This should never drop below VGS minus VT, VDS2, VDS2. So VO is VDS2, and this should never drop below VOV of this one, of Q2. So VGS minus VT. So the minimum output voltage here, the minimum voltage at the output node, rather, is VGS minus VT, so 1.008 minus 0.7, 0.31 volts. So as long as the voltage is larger than 0.31 volt, the output current would be almost constant. It won't be ideal because I have VA. It won't be fixed at 100 micro. It will change. So how do we measure how far we are from constant, from ideal constant? The output resistance is this figure of merit that we use. If it's infinite, perfect. This is a perfect current source. If it's not infinite, the lower it gets, the worse is the current source. I would like it to be as large as possible. So what is the output resistance in this case? The output resistance, we derived the formula for that, and it's equal to small r02, which is VA2 over half K prime, W over L2, VOV squared. Now, this is all of these quantities, I have them now. So VA is 20, and then 100 times 10, and I just calculated VOV to be 0.31, so 0.31 squared, and I get 208 kilo ohms for the output resistance. So 208 kilo ohms, this looks like a large resistance, so that should be fine. But let's answer the third question to see, is it really close? Is the output current really close to being fixed, or does it vary a lot? So the third question would be, how much would IO vary if the voltage at the output node increases by 1 volt? So if VO went, say, from 2 to 3, or 3.6 to 4.6, I have to be always larger. This voltage should always be larger than 0.31 to operate in the right region. So again, say VO increased from 3.6 to 4.6. That's a delta VO of 1 volt. How much would IO change because of this? So delta IO and delta VO are related by the output resistance formula. And the output resistance RO is delta VO over delta IO. So if I have RO and I have delta VO, I can find delta IO, and it will be delta VO over RO. So delta VO is the change in the output voltage, 1 volt. RO is the output resistance, and this means that if the voltage increases by 1 volt, the current increases by 4.8 microamp. The nominal current is 100. The nominal current is 100. And an increase in the output voltage of 1 volt would increase the current by 5 microamp. So that's 5%. So this is, I would say, a decent current source. And an increase of 1 volt in the output voltage would increase the current by 5%. That's not too bad. That's pretty good. And of course, if I can make the output resistance larger, then this increase in current would be smaller, and I will be closer to the ideal case. So now let's look at the current mirror circuit. The current mirror circuit is a circuit just like the one that we just analyzed, but instead of having the resistor and the reference current flowing in the resistor, I have a current source there, and the equation in this case would be exactly the same as on the previous slides. IO would be IRF times W over L2 divided by W over L1 if there's no VA, and if there is a VA, then I multiply by the correction factors. But the first time I looked at the circuit when I was a student, I was like, well, if I'm trying to build a current source, can I use a current source to build the current source? And if I want a current source, then if I have a current source, I just use it. And why am I building a current source and requiring that I have another current source? So that's kind of confusing. The reason we do that is, here I'm mirroring the current of a current source, and I'm building another current source based on the reference current source. So this one here, this is like a golden reference. This is a circuit. This will be a circuit. Again, there's no simple device that will give me a constant current. This will be a circuit, but this will be a complicated circuit that is well designed. A lot of effort is spent on designing it. It will be probably a large circuit, an expensive circuit, and I want to build it only once because of that. So I want to build this golden reference only once, and I know that it will give me a current that is almost perfect, constant all the time, no matter what. If the voltage changes, if the temperature changes, if the noise level changes, if the humidity changes, if the device parameters change, I want this to be always equal to IREF. So this will be a circuit that I don't want to repeat many times because it's large, expensive, and complicated. I build it once in my circuit, and then whenever I need a current source, I don't copy the circuit again. I'll just mirror it. And if I mirror it, I will get a current IO, which is equal to this IRF times a certain constant, the ratio of W over L's. And what is the additional circuitry that I would need to mirror IRF? Usually just one MOSFET. So adding a Q2 would give me the output current that I need. So let's say this IRF is my golden reference. And for example, let's say I built it and it's 100 microamp and it's perfect, ideal, 100 microamp, fixed, no matter what. Now, in another part of the circuit, I need a current source, which is 200 microamp. I will not go back to my design and change it and design it again and perfect it and build it. No, I would say, okay, I have the 100 micro reference. That's my golden reference. If I want any other current value, I will mirror it. So I would say, okay, IO is IRF W over L2 divided by W over L1. And this means that if I want a 200 microamp current source, I'll just use a transistor Q2, which has a W over L, which is twice the W over L of Q1. And what will be IO? It will be 100 times 2, so 200 microamp. Great. I built a new current source now. Oh, and what was my additional complexity? What did I need to do that? I just added a MOSFET. Let's say I want to build a current source, which is in some other part of the circuit. I need a current source, which is 450 microamp. Would I repeat the IRF and Q1? And no, I don't need to do that. I'll just take this and this. Where is this? And just mirror with another MOSFET. And if I make this W over L ratio of this Q3 4.5 times W over L of Q1, then the current here would be 4.5 times IRF. And again, to produce a new current, what did I need? Just one MOSFET. The additional MOSFET will give me the new current. And I can do this many, many times. Because if I connect MOSFETs like this, they don't really affect each other because there's no current into the gate. They just sense, they measure VGS, sense the value of VGS, and to produce a current as a result. So this is why we use this golden reference and we just mirror it. We don't build it again and again and again because this will be a very, very expensive um, proposition. So this is how we can build current sources. But if you look at the or consider the rest of the circuit, again, this is connected to some part of the circuit. This is connected to maybe another part of the circuit. If you consider these rest of circuit blocks, what we're building, what they feel is, so okay, this is the rest of the circuit, and what they feel is that the current is being synced. We call this is the symbol of an element called current source. But this really, as far as the rest of the circuit is concerned, this is a current sink because we're taking current out of the rest of the circuit. So we're sinking current towards ground. What if I want to build a current source that sources current into the rest of the circuit? So something like this, and it gives current, makes current flow into the rest of the circuit. How can I build a circuit that gives me this, not this? This is a sink, while this is a source. So any ideas how we can build a source, an actual current source that will source current into some circuit, not sink current from the circuit? What we will connect it to the supply so that we can get current from the supply in the direction of the circuit, and maybe using P MOSFETs, we can do that. So in fact, I can use P MOSFETs as shown here to build a current source that sources current into the rest of the circuit. So the rest of the circuit would be, in this case, connected here. And what does it feel? Now it feels that there is something. What is this something? The Q1 and Q2. The current is being sourced, given to the rest of circuit. So this is a current source. So now we know how we can build a current source and a current sink. And we can also build a current source and a current sink in the same circuit. So if I want to sink current from here, say, then I can build the circuit on the previous slide here. And this will give me a source pushing current into the rest of the circuit, and the sink taking current, sinking current from the rest of the circuit. So that's possible. Using P MOSFETs, I can build current sources that source current, and using N MOSFETs, I can build current sink that sink current, and I can have both in the same circuit to source and sink current at the same time. Here, there's also another question. What is the small signal equivalent circuit of this current mirror? The small signal equivalent circuit. Why are we asking this question? Why do we need to know what is the small signal equivalent circuit? Because this usually is part of an amplifier. And when we analyze amplifiers, we analyze them using small signal analysis. So if I'm doing small signal analysis on the whole circuit, I want to know what is the small signal equivalent of this this current mirror circuit, and how can I find the small signal equivalent of this circuit or any circuit? It's the same procedure we learned in 310. I eliminate the DC sources, and I replace the MOSFETs or any other devices by their small signal models, and I analyze. I see. I find the quantities of interest. So in this case, if I do that, what do I get? Um, if we do this analysis, we can show that we only get a small RO2. So the whole circuit, whether the one you see here with the P MOSFETs or the one on the previous slide with the N MOSFETs, When I want to do small signal analysis, I can replace it. I can remove it and replace it by just small RO2. So small RO2 of this Q2 or small RO2 of the Q2 on the previous slide where I'm sinking current. And that means that the small signal equivalent circuit of this current mirror or current source is very simple, just a small resistor. That's it. And in amplifier analysis, if I'm amplifying an amplifier circuit, if I'm analyzing an amplifier circuit, then if I see something like this current source as part of the circuit, basito, that's easy. That's even simpler than a MOSFET. It's just the output resistance of the output MOSFET. So small RO of the output MOSFET. We will rederive actually. We will rederive this in a coming slide if you want to see how we got this result. Okay, and now can we build the same thing using bipolar transistors? We can, and this is the basic NPN BJT current source. So a very similar structure to the NMOS current source. I have two bipolar transistors, and one of them has this short between the base and the collector, and that's very important. The two have the same, have their bases connected, and their emitters are grounded, so they're also connected. And therefore, the VBE is the same for the two transistors. So what kind of output current would I get here? Let's start by saying that Q1 has a certain emitter area and Q2 has another emitter area, AE2. So emitter area is like W over L for the MOSFET. It's a parameter that the circuit designer can control. You can make the emitter area bigger or smaller. So Q1 area of emitter is AE1, Q2 area of emitter is AE2. We will start first with a simplifying assumption. We will neglect the base current. We'll assume that beta is very, very large. If beta is very large, goes to infinity, then this means that if I'm in the active region and IB is IC over beta, so IB is IC over beta and beta goes to infinity, this means that IB is 0. So we'll start with this assumption that there's no base current, negligible base current, and that the transistors are in the active region. Now, for Q2 to be in the active region, it's VCE, which is equal to VO. This is VCE2 here. It's equal to VO. VCE should be greater than VCE edge of SAT. So VO should be greater than 0.3 volt. So as long as VO is large, this will be active. Of course, active if there is current flow in the circuit. And Q1, what about Q1? Well, because of the short circuit, and when this is conducting, any current VBE will be greater than 0.5 volt. This means that this voltage is greater than 0.5 volt, and VCE1, when this is on, would be greater than 0.5 volt. So I don't need to check that its VCE is greater than VCE edge of SAT because of this short circuit that forces VCE to be greater than VCE edge of SAT whenever there is current flow. So Q1 is fine. Q2 will be fine, will be inactive when VO is larger than 0.3. And I'm neglecting the base currents. So now I can use the equations of current in the active region. IC1 will be IS1 e to the VBE over VT, and IC2 will be IS2 e to the VBE over VT. And I'm using IS1 and IS2 because IS is proportional to the emitter area. Because the two transistors have different emitter areas, their ISs will be different. IC1 is also flowing in the resistor. So if there is no base current, this is IC1, and it will be the same as IREF. And IC2 is here. So IC1 is IREF and IC2 is IO. IREF is the current in R, and this is VCC minus the voltage at the collector of Q1, but this voltage is equal to VBE. So VCC minus VBE over R. Now let's take the ratio IC2 over IC1 to show that this is a current source. IC2 over IC1 will be IS2 over IS1, and this is the ratio of areas. So this is a constant ratio once the circuit is fabricated. This will be a fixed number. And what does this tell me? This tells me that IO will be IREF. IO is IC2, IREF is IC1. IO will be IREF, the current flowing in the resistor, times M, where M is AE2 over AE1, and that's a constant. And this is a great result because it shows that the output current is the reference current, which is determined by this part of the circuit, and it's fixed, times a constant. So therefore, IO is a constant current, and this is a current source. So that's a similar derivation to the one we did for the MOSFETs, and we obtain in this case also an output, or the expression of the output current looks like a constant quantity. But we did a few assumptions here, a few simplifications. Here's an example of an op-amp circuit with transistors, with bipolar transistors. This is a full op-amp. So this is the internal circuit inside an op-amp. Inside the op-amp, what's here for LM324, a popular op-amp, there is a circuit that looks like the one you see with many bipolar transistors, and you see the current sources. So this is another symbol for the current source. If you see the symbol, it means current source. So there is a 6 microamp current source, and this current source is sourcing the current into this rest of circuit. Now that's a source, pushing 6 microamp into the rest of the circuit. This is pushing 4 microamps into this BJT. This is pushing 100 microamps into this BJT. This is a sink. This is sinking 50 microamps from this rest of the circuit. So this is a BJT current sink. This is a BJT current source. This is a BJT current source. This is a BJT current source. So I have at least 4 current sources or sinks in this circuit. So how do I build these? I build them using also bipolar transistors, circuits similar to the one on the previous slide. But the one on the previous slide is really a current sink. And now we'll have to see how to build a current source that pushes current into a circuit. Before we do that, let's look at the effect of base current, beta. We assumed that the value of beta is infinite. It's not infinite, really. Maybe very large, but not infinite. So if I have a beta, then I need to modify my analysis. Note here that I changed the resistor and I replaced it by a golden reference. So we should be okay with that. We know why we see a current source IRF. This is like the golden reference that I use, and I mirror. I do it once, I build it once, and I mirror it if I want 3 or 4 or whatever number of current sources in my circuit. So if I have base current, if beta is not infinite, and I have these 2 transistors, Q1 and Q2 inactive, then the base current would be IC over beta. If the BJT is active, IC and IB are related by IC equals beta IB. So IB is IC over beta for Q2, and same for Q1. They will have the same IC if they have equal areas and same VBE, and they're matched. They will have the same IC, and therefore they will also have the same IB, IC over beta. So the current flowing down and the short circuit between collector and base of Q1 would be IC over beta plus IC over beta. So that's 2 IC over beta. And then if I do a KCL at the collector here, I get IRF equal IC plus 2 IC over beta. So IRF is no longer equal to just IC. It's IC plus 2 IC over beta. And IO is IC, and now the ratio IO over IRF becomes 1 over 1 plus 2 over beta. So if there is a beta, if beta is not infinite, then the two currents are no longer exactly equal. There's a difference of 2 over beta between them. If beta is large, beta is usually large, but and if if uh, beta is large, 2 over beta would be a small number, and then you can approximate 1 over 1 plus x when x is small by 1 minus x. So this is approximately 1 minus 2 over beta. So this is considered like an error term. This is the difference between the 1, which we would like to have just IO exactly equal to IRF, but it's not. And the actual term here, 1 minus 2 over beta. So 2 over beta is considered an error term. What if I have different BJT areas? What if AE1 and AE2 are not equal? So M is not equal to 1. In this case, I can show that IO over IRF will be M over 1 plus M plus 1 over beta. And well, we also neglected early effect. What if there's early effect? What if VA is not infinite? We can also account for that and correct the equations, and this is what we get. That's no longer a simple equation that shows that the current is constant, but and this is the general expression for IO when the emitter areas are not equal and there is early effect. And you see that IO now depends on VO, and therefore this is not an ideal current source. IO would increase when VO increases, and we can measure this non-ideality by estimating the output resistance of the current source, which we can show to be also small RO2 of Q2. So this is a simple BJT current mirror that we just analyzed. Again, this is a sink. This sinks current from the rest of the circuit. How can I build a source that sources current into a circuit? The answer is on the slide.
So
I can use
yeah, I was going to say.
P and P, and to do that, here's how we can do it. So from the supply, I will have my reference, and then a P and P BJT. Wrong order. PNP BJT reference, collector shorted to base, and then the current is mirrored by the other PNP, and this is the output node, and this is the output current, and this is the reference current, and this is some supply V, whatever, EE or CC, doesn't matter. And here I have the rest of the circuit, and the rest of the circuit is now feels like this current is being pushed into it. This constant current is pushed into the rest of the circuit, irrespective of what the voltage here is. So this is the implementation of a current source. This is a current sink that sinks current from the rest of the circuit, and this is a current source that sources current into a circuit. Yeah, so there's a question about the ground. This can be here. Yeah, of course, there's a ground in the circuit. So this is how we can implement a BJT current source using P and P, and the circuit is just like the dual of the NPN. The second question on the slide is, what is the small signal equivalent of the circuit? If this circuit is part, again, of a circuit, of an amplifier circuit where I need to do small signal analysis, what would be the small signal equivalent of the whole circuit? So I want to replace the whole thing, all of this, the whole thing, all of this in small signal analysis. I take this, I replace it by what? If we do a small signal analysis on this, then we can show that this will be just an RO2. This is the output node, and this is small RO2. Same for this. Same for this, the PNP1 also. It will be a small RO2 between the output node and signal ground. So again, the fact that we're using this as a current source does not complicate our analysis. Of course, an ideal current source will be fixed, and it will disappear when we do small signal analysis. Why? Because it's like a DC source. It doesn't have any signal component, and we set all DC sources to 0, so it disappears if it's an ideal current source. If it's not an ideal current source and we're doing small signal analysis, we see the output resistance of it. And the output resistance in this case is small RO2. So that's fine too. I mean, it's an additional resistor, and the circuit is not really a big deal. So similar to the MOSFET, we see the output resistance, which is equal to small RO2 of the BJT Q2.